So, good evening, students. We have been discussing from previous class regarding the so-called forced vibration or the of the system due to the forcing. And at present, we are trying to consider force in a more general sense, that even initial conditions, if we are giving that is giving some kind of transient response, or if there is a steady state force which gives the steady state response. Even we'll consider the base excitation also, which is prevalent in most of the automobile uh, because of the road undulations. And here we'll see that the formulation is more general initially, and we'll go for a specific kind of excitation once we cover the general derivations. Here in the general derivations, mainly you'll see that because it requires some kind of inversion of a matrix. So we will be avoiding that inversions or finding the inversions in these derivations in terms of the adjoint matrix. So that is more convenient for some kind of hand calculation. But once we have some kind of a tool, computational tool, then now even the inversion that is more convenient to do through the numerical tools. But for hand calculation, I think this adjoint technique is more popular. So today we will continue with this topic which we left last time. So we'll take now the simplest type of force, which is harmonic force. And that harmonic force is having these forces are acting at n locations. So there are n number of forces in the system, and all force amplitude is different, q naught j, as well as their frequency is different. So basically, these are the external force which are acting onto the system, and each is having some different frequency. In fact, this q naught j part is complex in nature for the present, the way we have represented. And once it is a complex quantity, we will be having the amplitude and the phase part of that, because the force is a vector quantity, so it will be having phase as well as the amplitude part. And and here, because as such the force is a real quantity, but here we have expressed that in terms of a complex thing, complex quantity. This is for mathematical convenience. Actually, the real part of this quantity will be having meaning to us because the force is actually real. But the imaginary part we can ignore once we get the response. So response also will be getting the complex form, and then the imaginary part of that can be ignored. But this complex form of the force gives some kind of convenience in the intermediate steps in the formulation. So because these are n forces acting at different locations onto the system, they can be put in a vector form. So this is a vector of n into 1 into n. And this is the same thing. So it is having n components, and R is having n frequency and n complex amplitude, force amplitude. Now, if we take, because our other quantities are there in the Laplacian domain, so if we take the Laplace of this quantity, so this, because this is quantity, Laplace of this formally, so this force in the Laplacian domain can be written as various components at different frequencies. So, and this has been put in a single matrix vector form of size that is n into 1. This is a vector. So is having this n components in that. So now if you go back to the representation of the response in Laplacian domain, this was the force, that's a joint matrix and Z matrix this. So force we represented by external force and the initial conditions. So present case, we are considering the harmonic excitation, external one. Initial conditions, we are ignoring because, as I mentioned, once the steady state force is there, even some initial conditions are there. After some time, the effect of this will dies out. The tangent will dies out. Only we will be left with the steady state part. So that we, so here on this particular thing, we will be substituting here in place of RS here. So you can see that response in the Laplacian domain is from here. The R bar is replaced by Q bar, and that is this. Okay, so because if you want to expand the joint matrix at different columns, because it's n by n size, so we can have n columns of this. Each is representing a vector of size n into 1. So if we substitute that in the previous expression here in place of the matrix, and this is also vector having n component. So if we multiply this, we'll get in the form of summation n terms, j is equal to 1 to n. Z is a constant thing, so this will not interfere here in the subscript, but A will be having subscript and Q and this capital omega will be having subscript J. Z is because we already seen that once we factorize this Z, we had this expression where omega 1, omega 2, these are the natural frequency of the system. Omegas are the natural frequency of the system. Capital omega is the excitation frequency that we need to see. So here in this vector Q, we have two type of poles. One is simple pole at S is equal to I capital omega J, where J can vary from 1 to n. So these are the simple pole. There are other pole at S is equal to plus minus I omega R. This omega R is nothing but the natural frequency of the system, which we obtain from the roots of this Z when we equate it equal to 0, where there again are a number. So this poles gives the starting transient response, and it is 0 when initial conditions are 0. If you're starting with the initial conditions with this steady state force, then the tangent part will be 0. This S is equal to I capital omega J, which is corresponding to the forcing is called steady state response. So this is capital omega is related with the steady state response, and these poles are related with the tangent, which we are not considering for the present case. So steady state condition, for steady state condition, if we do the inverse transform of this, this can be converted into time domain because we require the response in time domain. So we need to substitute this S is equal to I omega j. So here you can see wherever S is there, we are putting the S is equal to I omega j. And this particular term, when we do the inverse transform, that gives e raised to I j omega t. So this is the inverse transform of this term. Some more steps are shown in the subsequent slide. Uh, so the summation, again, we can able to put them in a matrix form because there are n terms. We can, because as we did here, we multiplied, did the inverse transform. Again, we are bringing in the matrix form. So this is a matrix form of the A and the vector form of the force in the time domain. Here, as I mentioned initially, we started with the complex form of the force, and we had the understanding that only the real part will be meaningful. So here also, the response once we have got only the real part solution we need to retain. The imaginary part will be having no meaning. So how we got inverse transform of this to get this expression? Few steps are given here in the subsequent slide. So this is the inverse transform of the QS bar. Once we substitute the expression of the QS bar here, same previous one. Now I'm representing, except this term, I'm representing as BJS because we are substituting for the steady state response S is equal to I capital omega J. So I'm retaining this term only. I'm combining that other terms in the BJ form. And now this particular term again, the BJS, I'm writing here, you can see BJ is represented like this, where using the partial fraction approach, this constant we obtain by substituting the S is equal to I capital omega J. So if we substitute that here, the BJS will give us this quantity, which we can substitute in place of this BJ here, this one, and the inverse transform of 1 by S, this will be e raised to omega J. That is this. Okay. And now this can be expanded because this can be expanded because this n terms. So I is equal to 1, j is equal to 1, 2, n. Then again it can be reassembled. So here again they can be reassembled, and this is A matrix, and this is the force vector, where this Z S we had earlier in the factorized form in this form, but now we are substituted for. So wherever S will be there, we will be substituting I omega here. So this is the same expression which we got in the previous slide here, this one. So now another case is there when we have the omega j, excitation frequency is equal to omega k, natural frequency. So that is a case of what will happen when omega j is equal to omega k. This is a resonance condition, and in this case, if you see here, the z. So if we substitute s is equal to I capital omega I 1, and if capital omega 1 is small omega 1, this will become 0. So that is a response will be becoming infinite because of that. This is called resonance condition. So here you can see that there are n number of excitation frequency, and there are n number of natural frequency. So if jth excitation frequency is coinciding with the kth natural frequency, so any combination is it will give the resonance. So we have taken one of the representative jth excitation frequency, which is coinciding with the kth natural frequency. So because of that, resonance is taking place. And at the resonance, we know that this whatever the response we obtained earlier, the steady state response, will not be valid because here at resonance case, what is happening? There are double pole S is equal to I omega j, and which is also equal to the natural frequency. So there is a double pole, and for this, the treatment for obtaining the response is slightly different. Maybe you can refer to the appendix B. Here, the transient response will be there, and I will. So here, if you see, so there is a response at the resonance, and what happens at the resonance? The response grow with time. So you can see that now the response is having the time term here itself. So as the time increases, the amplitude part of the response will be increasing continuously. So this particular expressions, how to get some steps have been here, the 2-3 slides, but I'm not explaining here. Maybe you can refer for more detail on the book on this appendix. So a few steps I have given here. Maybe you can go through it. This is a long expression. So okay, so I will come up through a example so that the things will be more clear to us what we are doing it. So here you can see that we have some kind of string is having two masses. Earlier, I think we have obtained equation of motion for such strings having mass and whatever the initial tension is there in the string, and it is subjected to a force F1. So the force is having frequency that is omega. So here you can see that is the same frequency. Omega is equal to 1.5 T naught by ml. So this is the frequency of the force which is there. That is a harmonic force of this kind, and F1 is the amplitude of that, capital F1, and omega is the force frequency which is given by this. So the aim is to obtain the steady state force response for both the masses. So how, because of this force, not only this will be having some vibration, but this also will be having vibration because this is a coupled system. So what is the amplitude of those responses we need to find out. There is no damping in the system, so the phase difference between the force and the response will not be there. So earlier, I think in the chapter 2, we derived the equation of motion for this, where y1 and y2 are the displacement of the first mass and the second mass in the transverse direction. That is the transverse direction. T naught is the initial tension of the string. L is the total length of the string. So, and then the force is acting in the one of the mass. So this is corresponding to that. So, and the second mass is having no force. So this is 0. So here, if some other force is also acting, F2, then this will take this place. But for the present case, only one force is there. So now, till now, we have been ignoring this particular part. Now, because of the force, now this is also having the non-zero term, and this force is given by this and is having this frequency. Now with the eigenvalue problem, because to solve the force vibration, we need to go first for the eigenvalue problem. So eigenvalue problem we already obtained for this in the, I think, example in the chapter 2. So this, if we take the determinant of this, we'll get the two natural frequency of the system. So now we can see this is the first natural frequency, this is the second natural frequency, and this is the excitation frequency. So now you can see this 1.9, this is 7.0. So there is no resonance condition, that is for sure, because this is away from the 1.9 below below to this both. So is what our excitation frequency is below the first natural frequency. So resonance condition is there, not there. So we will be obtaining the steady state response of this. Now with this, even the modal matrix we can obtain from previous eigenvalue problem. So this is the modal matrix. This is the first corresponding to the first natural frequency. This is corresponding to the second natural frequency. So because these both are positive, so that is representing the mode related to the first natural frequency. Here one is having negative sign. So this is an anti-phase motion between two masses. So that is related with the second natural frequency. So one way is directly we can assume the solution, the force vibration solution, as amplitude and the frequency same as the force. So here what is happening, we have the forcing omega, the response also will be having same frequency. So whatever the force we apply to the system, dynamic system, the system will have the same frequency of excitation. The amplitude of the two masses will be different. So that is represented by y1 and y2. They are not time dependent, only this time dependent term is this. Now if we take the derivative of this twice, because in the equation of motion we have that, so only this will get derivated and we'll get the minus omega square because of j is there, that is a the imaginary part of that, that is j square will give minus 1. So now we'll substitute this, the assumed response in this equation, and we'll try to get y1 and y2 from that, capital Y1 and Y2. So if you substitute this here, this is the mass matrix, this omega minus this will be coming here, then stiffness matrix as it is, and we have taken the common because this is common, and time dependent term ej omega t is common throughout the expression. Common here also, and the right side also is there, so that will get cancelled. So now you can see this expression which is not containing any time dependent term because it got cancelled in either side of the expression. Now this particular, what is our aim? Our aim is to get the y1 and y2. So this matrix summation of this, if we invert and pre-multiply by this vector, so we can get the y1 and y2. So you can see this is a inverse of this matrix and this. So this is the steps which I think in the previous general expressions we were trying to do the, there is adjoint and that kind of things. But here, if we can obtain the inverse of this, then directly we can able to get the response. So this has been obtained here, and then once we obtain the inverse, we are multiplied with this vector. So this is the simplified version of that. And 2 by 2 matrix is there, so always we can able to get the inverse, even the closed form relations are there for the 2 by 2 matrix, so that can also be used. So y1 and y2 is now given by this. So y1 will be this divided by this, y2 will be this divided by this. So this is the expression for this. Now till now I think we have not substituted omega, which has been given to us. So omega is given to us is this. So we can able to replace omega square with this quantity here. wherever the omega is there, we can substitute. So if we substitute, this will get simplified to this. So now if you see what is happening at this omega, both the y1 and y2 is having same displacement. So this is a very specific case in which because they have different mass, so we generally expect they'll be having different uh, displacement, but for this specific frequency, they turn out to be same. Y1 and Y2 are having same amplitude, which is given by this. Here, because Y1, if we go back here without substituting omega, so this expression can give us the resonance condition. How it can give? Because if we take, let us say, y1 is this and multiplied by this quantity. So when this will be 0, when this y1 will be infinity, when this denominator is equal to 0. So if we equate, because this is a common denominator for both y1 and y2, so if we put this equal to 0 and solve, we'll get 2 because this is a quadratic in omega square. So we'll get 2 roots of this, which is omega nf1 and omega nf2. So you will see that the same natural frequency which we obtained earlier in using the eigenvalue problem, same natural frequency here will get, because resonance condition is also same as the natural frequency coincide with the excitation frequency. So from that condition only we have obtained this. So this is the interpretation of the response at any frequency which is given here. If we take the denominator equal to 0, so that is the condition of resonance. For that, the amplitude will be infinity. So here, now we want to plot this response just to see how they look like. Force response, steady state response, how they look like. So this is the response, and here what we have done, we have plotted this non-dimensional term, the non-dimensional amplitude y1. One of them I have plotted, the y2 also can be plotted on the similar lines, and non-dimensional frequency. So here you can see that if we plot this, so you can see if we can take y1 out from this expression, and we rearrange those equations such that we get the non-dimensional form of this, and if you plot, we'll get this kind of plot. So now you can see that there are 2 spikes. One is this, another is this. And if you see the corresponding the frequency, that particular frequency, that is nothing but this 1.378. So that is approximately 1.38, and omega 2 corresponding to this spike is around 2.66. So these are the resonance condition. So correspondingly, we'll be having the frequency equal to the natural frequency. So these are the resonance condition. So you can see the plot is in the semi-log, because if you plot in the linear scale here, you'll get very high peak at this locations, others will not be visible at all. So that's why it has been plotted in the semi-log, and only the positive, the mod of that has been plotted, so that because in log we cannot have the negative number, so that will be invisible. So the mod of that has been plotted here. So, and this is called resonance. This is called anti-resonance. So what is physical meaning of this? In the resonance, our amplitudes are becoming very high. Anti-resonance, where amplitudes are becoming very low. So why it is happening? So generally, often it is take place between two modes. What happens ki the contribution of the first mode is having some sign, let us say positive. The second mode is having negative sign. So uh, those two terms will get cancelled at some location here. So because of that, this is becoming very equal to 0. So this is called anti node, and that is having not much practical problem here. Only problem is the resonance, because there the amplitudes are becoming more, so we'll be having more issues here. And uh, this is also having importance in the sense that when we design any dynamic system, generally we design between two modes. So the excitation frequency of the system will be somewhere here. So we take the advantage of this, that I gave the example of the that is tempo, in which here at below resonance, first resonance, the amplitudes are larger. But once we cross the first natural frequency, then the amplitudes are becoming less and less. And if we can design such that if you have anti-resonance, that will be the best. So it will be more stable operation of the vehicle in this zone. So this is the typical plot of the force response, because if we are not considered the damping here, so the phase part we are not plotted. So actually this is called Modal plot, in which not only the amplitude versus frequency we plot, but also the phase versus the frequency we plot. And generally, if you remember in the um, this is I think 2 degree of freedom system, the phase or the single degree of freedom system, phase changes it at resonance. So the phase which is there uh, at before the resonance, at resonance it becomes 90 degree, and after that it becomes 180 degree. So that has that we are not plotted here, the phase part. But if damping is there, then that is more meaningful to have the plot of the phase also along with the frequency, and that is called Bode plot. So this is one of the example, and whatever the calculations I have done here is there in the code form. Even if you see, I try to do everything in this, even the derivation of the equation of motion, and then eigenvalue problem solution, then force response, inversion of the matrices in the symbolic form, and plotting of the response also. This you can use it for your purpose in case you're solving this kind of problems in the assignment. So this is a typical output. Okay. So if you have any query till now, then you can ask. Otherwise, I will take up the next one. Okay, if you have any query on till now. Okay. So just 30 seconds. Okay. So once we obtain the for harmonic motion, harmonic excitation, now next is the periodic excitation. So periodic excitation is what? Periodic excitation is when the excitation pattern is changing over interval of time. It is repeating or repeating after some period of time. That is called periodic. And we know the periodic signal. So this is the mathematical definition of the periodic signal, that after time period t, the the this particular force becomes same. So it repeats after a time. Like I can give the example of a, let us say, reciprocating engine. So there, if this 2-stroke or 4-stroke, we expect that whatever the force is there, that will repeat in that particular cycle. So that is one example for the periodic force in the system. And the frequency of that particular fundamental frequency of that particular force can be obtained using this. But such periodic force will be having multiple frequency, and the higher frequency will be integer multiple of the fundamental excitation frequency. And we know that we can able to obtain for any periodic function using Fourier series various harmonic components. So we can able to use Fourier series to split the periodic function into its the fundamental frequency and higher harmonics, sine, cosine terms, or this has been written in a complex form. So this is also similar to the real form of the Fourier series, but only thing is it's combined in the form of complex form. So here this is the amplitude part. P is the number of harmonics, which can be, because of the complex thing, is going from negative to positive. And this part, the amplitude part, can be obtained by this, which you're familiar with, where this tau is the dummy variable and AP is the complex amplitude of the Fourier series. So what is the advantage of this? So once we have this, what is happening? We have split the periodic excitation into number of forces having different frequencies. So that means when we are talking about a system having n number of forces, each force we have split into number of frequencies. So we'll be having at different masses so many excitations. So if we come back here, so you can see that at each station we'll be having n number of forces, and each force will be having so many harmonics in that. So what we need to do in the linear system, basically, one way is we can able to take one force, one harmonic, and obtain the response. Then take the same force, second harmonic, obtain the response, third, like that. So once we exhausted with that particular force, we'll take the another force and it's harmonic one by one. And the summation of all those response will give us the total response. So this is the same thing. You can see that we are summing up all the harmonics. So we have already obtained for one harmonic force in the previous exam. Before the example, we have taken harmonic force, and this was the expression for that. Now we are summing up that particular harmonic force for different frequencies from p is equal to minus infinity to plus infinity. So this is the force now, which are there not only at different masses, but their harmonics are also present. So we are summing up. You can see wherever the omega is there, p is also there. That means we need to sum all those terms and to get the total response of the system. So here generally all practical purpose p will not be infinity, depending upon the the type of force. We will see that if the amplitudes of the force is minimum or very less after some harmonics, we ignore those terms. So theoretically we can keep infinity, but practically after some harmonics we need to ignore those terms because the contribution of those forces will be less and less in the system. So now the same expression which we obtained earlier for a single harmonic force has been utilized to obtain for all the harmonic force. And again, that can be combined in this form. So here you can see the same thing. Initial conditions we are ignoring because this force we are expecting is a steady state force. And this is now a summation of various harmonics. Earlier it was single frequency, now is having several harmonics. Okay, so this was just extension of the harmonic force, how we can able to use that for the periodic excitation. So here only thing is we need to take more and more number of terms in this. So if we go back to the example which I explained, so here if we are talking about this excitation, so we can have a system in which this F1 e raised to omega 1 or t is there plus F2 j omega 2 t is there like that. So in that particular case, we can take one force at a time, obtain the response, second force at a time, obtain the response, and then add them. Because this is a linear system, superposition theorem is valid. So whatever the response we obtain, this for one frequency, we can add for another frequency to get uh, the total response for both the force of the component. Uh, in most general case, if we have F2 also is having also different frequency, that also can be tackled because here we'll be having that particular thing. So that I'm leaving it to you. If this is F2 is also there, how these expressions will take up. Periodic excitation is over. So now comes the so till now we have been dealing with the discrete system. This modal analysis for discrete system we are considering. This is actually when we have the large degree of freedom system. And then whatever I explained in the previous example, that just by inverting a matrix we can get the response. So some limitations are there in that. Or when we have this force which is not harmonic. So in the previous case, force was harmonic. So we could able to eliminate the time dependent terms. I will go back again to give this particular. So here we assume the solution in this form, substituted, and we found that we could able to eliminate the time dependent terms from here. But if this forcing is not harmonic or not periodic, if this is general force like step function or some other kind of functions are there, then we cannot get this kind of simple expressions. So in that particular case, what we need to do, we need to use modal analysis to convert this coupled equations to uncouple this. So this, using this modal matrix, we need to uncouple this. And once we uncouple, we'll get two single degree of freedom equations and with the forces, so that we need to solve using the Duhamel integrals. So that I'm explaining now. So modal analysis we for the discrete system. So here force is there. Till now we have used the this kind of transform. So using eigenvalue problem, we can able to get the modal matrix, that is we know. So the modal matrix can be used to transform this particular generalized coordinate to natural coordinates. And if you substitute this in the equation of motion, so the Q is replaced by this here, and then we the U transpose both sides. So we multiply T transpose this. So now we know that if we are normalizing the mass or the modal matrix with respect to the mass matrix, this becomes an identity matrix. this becomes the square of the natural frequency. So this is the identity matrix. This is the square of the natural frequency. Only diagonal terms are there. And N is the force. So N is called generalized force here. So you can see N is represented by this. So this is generalized force. So this is an imaginary force which is acting in the those uncoupled equations. So now if you see if we substitute this in the equation of motion, we'll get the equation of motion like this, because this is identity matrix. So this is uncoupled equations. Any issue? Okay. So this is the uncoupled equation. So we can write them like this. So these are this is single degree of freedom system, but n in numbers. So earlier equation of motion was coupled single system having n degree of freedom system. Now, because of the modal matrix, we could have uncoupled them. So now you can see this generalized force, which is an imaginary force acting in that particular single degree of freedom system for rth mode. So this is imaginary generalized force which is acting on the this, and this we already expressed in terms of the actual force like this using the Modal matrix. So this we know, if the force is of general nature, we can able to solve this using the Duhamel integral. Very first chapter we have been doing this. So this is the modal analysis for discrete system and continuous system. So in discrete system, we have single system with n degree of freedoms. They are coupled. Using modal analysis, we break them into n number of systems with each 1 degree of freedom system. So we have seen in the previous slide that we have n number of equations of single degree of freedom form, and they are n in number. In the continuous system, we have single system with infinite degree of freedom system. Infinite degree of freedom. Using modal analysis, we'll see in the subsequent lectures, we can able to convert the single continuous system to infinite number of systems with each 1 degree of freedom system, 1 degree of freedom. So this is the very abstract representation of the modal analysis. So coming back to that particular equation which we got, so if we do the Laplace transform of that single degree of freedom, this Laplace transform of this, earlier also we did it. So this is from the acceleration term, this is from the second term, and this is the force. So this is in the Laplacian domain. Now we can combine the similar terms, and remaining the initial condition thing, we can bring the right side to get this expression. Now the response is this. So if we divide by this quantity, we can get the response like this. And if we do the inverse transform of this, this I think we have done earlier also. So this is convolution integral, and with the initial conditions here. So this is the transient part if we are considering, and this is the steady state part. Now this is for the undamped system. We have, I think, even the assignment you have done for the damped system also. So this is the same convolution integral. So now you can see when the force is not harmonic, then we need to go for this kind of convolution integral to get the force, the generalized response because of the generalized force. This is the natural coordinates. So once we get these are the initial conditions which we can get. This is generalized coordinate. This is the natural coordinate. So because we have transformed the equation to the natural coordinate. So initial condition also we need to transform in this using this. Now once we get the natural coordinate response, we need to bring back this into the actual coordinate using the model matrix. So model matrix, this is the first row, second row, and nth row. If we split this natural coordinates like this, if we multiply, it can be written in the series form. So this is the ith eigenvector, and this is the eigen-natural coordinate. And this is given by this. So our response we can able to get from this, because so we need to substitute this here and multiply with the eigenvectors to get the actual response. So I'll stop here, and then maybe in the next class I will take up example for this modal analysis. Same example, but with two forces. I will explain this modal analysis. Because of the because I could have taken the bigger size matrix for this, but for illustration purpose, I'm just considering only the 2 degree of freedom, so that you can appreciate the method, but detail for bigger matrix will remain same. It will not change, because anyway we express them in a form of matrices. So once we are expressing in the form of matrix, the size does not matter. So I think there is a question from Rakesh.
Hello.
Rakesh, yeah.
Hello.
Yes.
Sir, my doubt is regarding the assignment number 6. Uh,
Yes.
sir, I got one beam problem, and I have to solve that problem, and I got the fixed end condition. So it is the beam problem. So means at both the end, the slopes and the deflection is 0, and I have to find the the function which satisfy the boundary conditions. But sir, I am not able to calculate that function. So I'm sitting there. So means my doubt is, means I'm not getting the function which is differentiable at giving the value 0, when differentiable at x equals to 0 and x equals to L. Means I am satisfying the only 3 conditions. One condition is always violating, sir.
So you're trying for comparison function?
Yes, sir. Comparison function.
Anyway, for this case, all are geometrical boundary condition, no?
Conditions, sir. Yes.
So solution is not easy. You need to work on that. So what you can do, because if you can take because we are already, I think, solution for the that kind of system, closed form solutions.
Okay.
So one is maybe that eigenfunction itself is available to us.
Okay.
So that can be taken as a starting point, even for the approximate method. Okay, but I'll suggest you try out some something, some polynomial which satisfies that. You try out. That is the purpose of the assignment, that you try something.
So otherwise, can I can I solve that one with the collocation or Galerkin method? So that means there we we choose the function. Means it is not necessary it should satisfy the boundary condition or differential equation also.
Yeah. Collocation method you can use, but Galerkin method requires comparison function.
Okay, sir.
Yeah, that you can try out, but you will face difficulty in the eigen function there. No, eigenvalue you can get it, but natural frequency you can get it, but you will face difficulty in interpretation of the mode shape, because your matrix will not be symmetric.
Okay. So, since I tried for the polynomial function, as well as the combination of the polynomial function and the trigonometric function too. But means three
So,
conditions are satisfying and one condition is not satisfying, sir.
best is share this your whatever you've done it. No, share it,
Okay.
then I can help you.
Okay, sir.
Yeah. Yeah, Abhishek, Rakesh.
Yes, sir. Good afternoon, sir.
Ah,
So my doubt is also on assignment. Sir,
ah.
I have gotten a beam problem. In that, I am getting both the boundary condition with eigenvalue only. So to check for the self-adjoint, sir, like with the expression we are using is integral over d, u, lv, dd, and the summation.
Share it, no? Share why you are, how I can understand DDD you are talking about, no? So you share
Like,
this, you have been, I think, emailing me. So
yes, sir.
this also you emailed.
Okay, sir.
Okay. It cannot be, I cannot
Yeah.
understand what you are talking and, because there are 50 questions. I'll not able to answer all of them. No,
Okay, sir.
because these are all, it's not something like you just start solving. You need to think,
Yes, sir.
you need to think. So you give in the slide, then I will reply.
Yes, sir.
Yeah, with the
Thank
best
you.
way to.
Yes, sir.
Hello.
Yes. Who is there?
So I forgot to ask you one thing, sir.
Ah,
In that problem, that beam problem,
hmm.
the compressive axial force is given, sir. So in case of the formulating the eigenvalue problem, should we have to consider that one or neglect the external forces? Means as we discussed.
I'm not getting. Again, you repeat.
So means in my problem, the
Hmm.
beam having the transverse load, axial compressive load, and that beam is resting on one foundation having the stiffness K. Okay. So while formulating the eigenvalue problem, we have to neglect the compressive load, or we have
No,
to
no,
take
no,
that.
no, 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 no. That is a part of the system, like a string problem. No, is having
Okay.
initial tension. You cannot ignore that. That is
Okay,
not a,
sir.
that is not the dynamic force. That is a initial tension. Like in a spring.
Okay,
In a
sir.
spring, if there is initial tension, that is a different. That is a you cannot ignore that initial tension in the spring. Because of some constraint in the beam that has been given. Or like if you're talking about the base foundation. So
Hmm.
railway, the rail is there. So lying on a some foundation which is flexible. So while analyzing, you cannot ignore that. Huh?
Okay, sir.
Yeah. So that is the example of a rail in which is lying on a some, that now concrete, uh, I think sleepers they call it. So when the rail moves, it it is having flexibility. Okay, you must have seen the rail
Okay, sir.
goes up and down because of when the train passes. No, so if you want to analyze such system, you need to consider you cannot ignore those things. Okay.
Okay, thank
Okay. Okay. So I'll stop here and think.